Hello, the next question we have on this exam is question 3, which says, consider the left-leaning red-black tree below. All nodes/links are black. Show the steps in the tree for delete 7. So, in general in red-black trees, we have 5 different properties of red-black trees. I'm going to go through them real quick. The first property that we have is the node property. The node property tells us that each node is either red or black. Pretty simple. The root property is next, and the root property tells us that the root of the tree always has to be black. The root equals black. I'm gonna try to make a little image representation for each of these. So, next property we have is the red property, and the red property is that red nodes so I'm going to write this in red. Red nodes cannot have red children. Red nodes have to have black children, or no children. The fourth property is that every path from a node to its descendant null nodes has to have the same number of black nodes. That means I don't know how to write this. Number of black nodes are equal among all the paths. The fifth and final property is that all leaves, which are the nil nodes, are black. The nil is just something that has to do with that each of these nodes are connected to one nil node, technically. And so it's saying that that nil node is black. That's not necessarily super important for us right here. So, the question that it asks us here is, show the steps for delete 7. Now, deletion is a process that is very difficult in a lot of different binary tree operations. Specifically in left-leaning red-black tree, it can get quite complicated. We'll see that in this particular problem, it actually the test proctors were aware of the fact that it's going to be difficult to make deletions, and so they made this particular one easy, such that the left-leaning red-black tree here, when you delete 7, you are going to not have to make a lot of changes, and I'll show you why. So whenever you make a deletion from a tree, the goal of the deletion is there's 2 steps we'll do in the deletion. The first step is going to be replace the deletion, the node to be deleted. I'm going to call it the del node, with the next in order value. And then the second step is going to be delete old value and rectify. So what I mean by that is that we are going to take the 7 and we're going to replace it with the next in order value. And so what that means is, in a computer sense, it's going to be the leftmost value in the right subtree. And in a physical sense, it just means it's the node that is closest but more than the 7. So we're going to go to the right subtree and we're going to find the leftmost node, and we find it to be 8. So in other words, we're going to replace the 7 with 8. That's our first step. That's all we have to do for the first step. The second step is to delete the old value. So we're going to delete the 8, and we're going to rectify the tree. Rectify the tree means that we need to basically check all of the rules for a tree, and we need to verify that all of those are still true. So, for one, we need to see, are all the nodes either red or black? Yeah, they are. Is the root node black? Yes. Are there any red nodes that have red children? There aren't any red nodes to begin with. Are the number of black nodes equal on all paths? We can verify this by looking at each path. To a leaf node, and we see that each path still has 4 black nodes total. And the last thing is that all null leaves are black. So, in other words, what we're seeing here is that by replacing the 7 with the 8, and just getting rid of that old 8, we have created a tree with the 7 deleted. This process can be much more complicated when you have red nodes and you have to shift and rotate things around in order to achieve a correct tree, but for this particular problem, that's not required. Today we're going to be looking at the Spring 2022 exam from CS 251. We're starting on question 2 because question 1 was already answered on a previous video. Question 2 states, show the state of the left-leaning red-black tree and the corresponding 2-3 tree after the following operations, and then it gives a series of inserts. In CS 251, there are a concept known as B-trees. B-trees are some kind of a tree that has a max order or a max degree. The main 2 max degrees that we work with is degree 3 and degree 4. Degree 3 typically goes with 2-3 trees, and degree 4 goes with 2-3-4 trees. The whole idea of these trees is that it is a type of tree that looks similar to a binary tree, except that each node can hold more than one value. So for example, in a 2-3 tree, each node can hold up to 2 values, such that each node is called a 3 node. It can have 3 children. And so we end up with trees that look kind of like that, where it can have more than one value per node. Then we can also have 2-3-4 trees, where we can have 3 different values per nodes, ending up in a 4-tree pattern. So we could have something like this. Zero, 2, 4, 6. So each of these, this is the 2-3 tree and a 2-3-4 tree on the left and on the right. And these types of trees are really helpful for organizing values. However, they aren't super helpful in terms of the actual computer representation of them, in that it is usually better to have things just set up in a normal binary tree where there's only one value per node, because then we don't have to keep track of multiple nodes or multiple values per node, and we also don't have to keep track of how many values are in each node or what kind of node it is. And so instead of having 2-3 trees and 2-3-4 trees, we usually take this representation and we turn it into something called either a red-black tree or a left-leaning red-black tree. And the whole idea of a red-black tree and a left-leaning red-black tree is that it essentially takes the exact same 2-3 tree and 2-3-4 tree that we had before, but it turns those nodes that have more than one value per node into separate nodes. So for instance, in the case of a left-leaning red-black tree, we essentially take all of the 3 nodes, so the nodes that have 2 values, and we split them up into a black node and a red node. And so for a left-leaning red-black tree, as the name implies, we're going to be putting the red node as the left child. There should be one left child at most that's red for these trees. So we'll have something like this. I'm going to put the red nodes in a triangle just to show their difference. So the above tree that we had, the 3, 5, 1, 4, 6 tree, is the exact same as this left-leaning red-black tree that we have here. This is the left-leaning red-black tree representation of the 2-3 tree. And so what we have is that we took the higher of the 2 values in that 3 node, and we set that as the black node, and then we set the 3 to be the left node, to be the left red node of the 5 node. And so then we take the low value, which is the 1, and we set it to be the left child of the red 3. And we take the middle value, and we set it to be the right value of the red 3. And we take the high value, and we set it to be the right child of the black 5. You may notice that this new representation turns into just essentially a normal binary search tree, except that now we have red and black nodes. And so a left-leaning red-black tree and a red-black tree are essentially just binary search trees, but with a constraint on the color of each node, and that allows us to do some balancing. Similarly, with a red-black tree, this doesn't, the red-black tree allows us to have red nodes as both the left and right child of a black node. And so we can have something like this. This would turn into a parallelogram. Oops. 0, 2, 4, and 6. So these left-leaning red-black trees and red-black trees have a couple different rules, and you can look those rules up in the lecture notes. The main rules that I'm going to state here are that a red node cannot have another child that is a red node, and that makes sense because we said the red nodes are just kind of showing that they are the side values in a 2-3 or a 2-3-4 node that aren't the main either the middle value or the higher value. So what I mean by that is that the 3 here is what we turned red, and the 1 and the 5 here is what we turned red. And so essentially, if we were to have if we were to add a 0 into the node here, we would end up adding the 0 as a red child to the 1 down here. And so in other words, the red nodes in the left-leaning red-black tree and the red-black tree won't ever have a red child. Another important note is that every path that you take through the red-black tree and the left-leaning red-black tree should have the same number of black nodes, and that's in general how we keep these trees balanced. And the whole advantage of them of having a left-leaning red-black tree and a red-black tree over a binary search tree is that we can keep the height of the tree to be as low as possible, generally speaking. And so in the left-leaning red-black tree, we can look and we can see that we've got through this path, let me highlight it. Through this path here, we have 2 black nodes. Through this path here, we have 2 black nodes, and then through this path here, we have 2 black nodes. Let's say through this path, we have 2 black nodes. So in every single path here, we have the same number of black nodes, and that's one of the other constraints that we have about these trees. So let's get back to the actual question at hand. I'm going to take all this and minimize it to the side for reference later. All right, so the question here is, again, I'm just going to repeat it real quick. We are supposed to show the state of a left-leaning red-black tree and the corresponding 2-3 tree after each of the operations. So in general, you can insert things directly and look at them as a left-leaning red-black tree from the start. Like you could insert 3, 7, 2, 9, 0, 11, and 1 into a left-leaning red-black tree and just add them right there. But doing that requires you to do some different rotations, and I personally find that a little bit more complicated. And so what I would recommend to you is if you struggle with the left-leaning red-black tree and the red-black tree rotations and insertion, things like that, it typically is just easier to make it as a 2-3 or a 2-3-4 tree and then convert it into a red-black tree afterwards. So that's what I'm going to do here. We're going to go along each step, creating the 2-3 tree first, and then we're going to change it to the representation of a left-leaning red-black tree afterwards. So first we're going to do our insertion of 3. Let me quick label these. We're going to have 2-3 tree. We're going to have the left-leaning red-black tree over here. So we insert a 3 node into the 2-3 tree, and again, the exact same thing happens in the left leading red-black tree. That's not super complicated. It's just a normal black node we insert first. Next, we insert a 7 into the 2-3 tree. And so in the 2-3 tree, that means that we are going to now be... means that we are now going to be adding a second value into this node, and so that turns from a 2 node into a 3 node. Again, remind ourselves that it's called a 3 node because there can be 3 children that come out of this. So we've now got a 3 and a 7 in this 2-3 tree. And to change that representation for the left-leaning red-black tree, we now look at it as one of these two values is the black node and the other one should be the red node. Now, in a left-leaning red-black tree specifically, we always have to have our our red nodes as the left child. And so we set the 7 to be the black node, and that way we can have the 3 be the red node. You may notice that in the question it says to use solid lines to use black to represent black nodes. It does that because you likely won't have red and black on the test, like a red pen and a black pen on the test. I'm just going to represent it like this for clarity's sake, but always abide by the formatting that the test wants you to use. So next we insert, so let me cross these off real quick. We've done inserting 3, we've done inserting 7. Next we insert 2. To insert 2 into this 2-3 tree, we're going to insert it into the top node that we have here. And again, we're following the number order as we go, so that it's 2, 3, and 7. And now you may see that we no longer have a 3 node, but we've turned into a 4 node. And so the whole idea with 2-3 trees is that we can only have a max a degree 3 node, and so we have to turn this 4 node into split up nodes. And we do that by raising up the middle value of this 4 node. So in other words, we're essentially going to move the 3 up, and we're going to send the 2 and the 7 down to be their own side nodes. Then to match the representation in the left-leaning red-black tree, we're going to look at this and we're going to see that because of the fact that we only have 2 nodes in the 2-3 tree, we may as well just only have black nodes in the left-leaning red-black tree. And so we end up just having a position like this, where they match each other identically. That's an important thing to notice, is that whenever you have just a single 2 node in your 2-3 tree, or a tree made up of 2 nodes, they are going to look like, it's going to look like the exact same tree in the left-leaning red-black tree, because a 2 node just represents itself as a single black node in the left-leaning red-black tree. Next insertion, we've got 9. To insert 9, we're going to treat the 2-3 tree like a normal binary search tree. We're going to look at the root node, and we're going to say, is 9 greater than 3 or is 9 less than 3? 9 is greater than 3, so we go to the right subtree, and we look at the 7. And because 7 is a leaf, we go ahead and just insert the 9 in with the 7. We abide by the order in there so that the 7 is to the left of the 9. Now we want to match the left-leaning red-black tree representation. And again, in left-leaning red-black trees, the red node always has to be the left child. And so that means that we have to have the 9 be the black node in this case. So we set the 9 there, and we set the 7 to be the left child. Next, we're going to insert 0. 0 is, we're going to compare it to the 3. 0 is less than 3, so it goes down to the 2 over here, and it joins the 2 because the 2 is a leaf node. Remind yourself that a leaf node is a node with no children. And so that's a very large node. We put the 0 to the left of the 2. Again, we need to match this representation with the left-leaning red-black tree. And so we're going to, again, have the second value, the left value in this 3 node be the red value. And so we have the left child of the 2 in the left-leaning red-black tree be a red 0. Next, we're going to insert 11, and I want to real quick resize these because they are starting to overtake each other's area. Let's hope I can write that small. All right, next we're going to insert the 11. This is where things are going to get a little bit complex, so stay with me. So the 11 is going to be more than 3, and so we're going to insert it with the 7 and the 9. Insert it with there. Now again, as we had before when we had to split things, we have a 4 node now, and we can't have a 4 node in 2-3 trees, so to fix that, we're going to shift the 9 up, and we're going to send the 7 and the 11 down. Now, when we originally had done this process, we, let me try to remember, we did it with 2, 3, and 7, and we sent the 3 up to be by itself, and we sent the 2 and the 7 down. It's a fairly simple process there, because of the fact that there is no node that the 3 is going up into. However, when this 4 node right here sends the 9 up, the 9 isn't going to go by itself, it's actually going to join the 3. And so we're going to end up making our new tree 3 and 9 together. 0 and the 2 are going to stay together on the side. And then there's going to be 3 children here. One of the children is going to be 7, and one of the children is going to be 11. And so essentially what we've done is we've sent the 9 up, we've set the 7 to be the left child, and we've set the 11 to be the right child. Or I guess the 7 to be the middle child. If you're ever worried about that your tree does not abide by the correct laws of 2-3 trees, just go ahead and look at it again and make sure, in general, the keys should always be the values in between the children. So what I mean by that is that the 3 and the 9 here are keys, such that the 3 should be greater than all the values over here, but less than the values over here. The 9 should be greater than the values over here, but less than the value over here. So that the 7 should be in the middle of them, the 11 should be greater than both of them, and the 0 and the 2 should be less than both of them. We see that we have that here, so we know that we did the process correctly. All right, next we're going to look at our left-leaning red-black tree, and we're going to match the representation. I'm just going to go ahead and delete this because we're going to have to make quite a few changes. So we see our top node with 3 and the 9. The way that we represent that is, as we've done before, the higher value in the left-leaning red-black tree is the black one. The lower value is the red one. So we have our 3 and our 9. And so now the way that we're going to set the rest of these up is that we're going to have the 11 be the right child of the 9. The 11 is going to be black because it's by itself. The 7, this is a more tricky one here. The 7 is going to be the right child of the 3. And the reason for that I will show in just one second. And then we've got the 2 that's the left child of the 3, and the 0 is going to be the red child of that. So the reason that we have the 7 be the right child of the 3 is because the 7 according to our 2-3 tree, is supposed to be between the 3 and the 9. And that makes sense number-wise. 7 is between 3 and 9. And so because we can't really have a value in between 3 and 9, what we do is we do the next best thing and we send it to a place that is greater than 3 but less than 9. So it's kind of in between that middle space. Continue to make my trees too large. Shrink this up a little bit. All right. We have our last insertion. It is 1. So our insertion 1 into our 2-3 tree is going to be less than 3 and less than 9. So it goes to the leftmost zone and joins the 0 and the 2 so that you get 0, 1, 2. Once again, we have a 4 node now, so we need to fix this by sending up the middle value, 1, into the nodes above. And so we're going to send up that middle value, just like we did with the 7, 9, and 11. And it is going to make this top node be 1, 3, 9. And again, we're going to have the 0 and the 2 split on the two sides of the 1. Going to have the 7 in the next over node and the 11 in the other node. Now, one thing that you may be noticing is that, hey, this is still a new 4 node that we've created on the top. The 1, 3, and the 9 should not all be together in a 2-3 tree. And you're correct, so we need to do this process again. We need to now send up the middle value, which is the 3. That's too large. Send up the middle value, which is the 3, to be by itself. And the left child to be the 1, the right child to be the 9. Left child of the 1 is 0, right child of the 1 is 2, left child of the 9 is 7, right child of the 11 is, of the 9 is 11. I'm going to show why this is all the case real quick. So we know that we're sending our 3 up to the top. And so, in other words, we can kind of just look at where these other values, don't know what that did, where these other values go in respect to that, in that our 1 gets cut off here and joins the 0, it has the 0 and the 2 as children, and then our 9 has the 7 and 11 as children, and 3 goes up. Does that make sense? I'm going to assume you said yes, because I can't hear your voice saying no. All right. Last thing we need to do is turn this into a left-leaning red-black tree. And if you have been listening, you will know that this new 2-3 tree we've made is going to be super easy to turn into a left-leaning red-black tree, because this 2-3 tree that we've made is entirely composed of 2 nodes. And what does that mean? That means that we have no red nodes in our left-leaning red-black tree, because red nodes are created due to having 3 nodes or 4 nodes. So in other words, we just have the exact same tree, but black. All nodes are black. This is the left-leaning red-black tree and the corresponding 2-3 tree that we get after all these insertion operations. If you were doing this question on the test, you should be keeping all of the trees after each insertion and showing that along the way. Hello everybody, today we're looking at question 4 from the exam. This question is a bit long, so bear with me. We're going to try to get through each of the parts of it individually. This question says, let G be a graph represented by the edgeless below. G is connected, undirected, and weighted. I'm going to clarify what all those terms mean real quick. Connected is the term that we use for a graph that has all of its vertices connected by some path of edges from one vertex to another, and that you could pick any vertex U and any vertex V in the graph, and you could find a path to get from U to V. And so, in other words, there are no vertices that are isolated from the others without an edge to them. Undirected means that all of the edges within G are bidirectional, or undirected, however you want to look at it. The point being that you can traverse from U to V. If there's an edge between U and V, you can traverse from U to V, or you can traverse from V to U using that same edge. It doesn't have a certain direction that it has to go. Then weighted is the last term that we have here, just to signify that each of the edges in G has a weight associated with them, has a cost to traversing that edge. And so we'll see that we'll be able to use that in a couple different algorithms here for these questions. So then it gives us an edge list, and it says each tuple UVW represents an edge between vertices U to V with the weight W. And so what that's saying is essentially, if we're looking at this first tuple here, the first term, 1, and the second term, 2, are the two vertices that it's connected between, and then the third term is the weight. So we're going to draw this out as we go. So looking at the first tuple, we see that there is an edge between 1 and 2 of weight 4. That's implying that there is a vertice 1 and 2. We can just assume that because of the fact that it says that there's an edge between them. Next we have 1 to 3 of weight 6. Next we have 1 to 4 of weight 7. Oops, sorry. 1 to 4 of weight 7. Next we have 1 to 5 of weight 5. We have 2 to 3, I'm going to wrap that around, of weight 4. We have 3 to 4. Oops. 3 to 4 of weight 3. We have 3 to 5 of weight 6. And we have 5 to 4 of weight 4. I'm going to real quick rewrite the 3 down here just to signify that it's part of this edge and not one of the neighboring ones. All right, so that is our graph that we have. So now we're going to look at some of the different questions here, and we're going to try to figure out what our answers will be. So the first blank that we have here, highlight it, G has blank distinct minimum spanning trees. So this is another concept that I'm going to clarify real quick. A spanning tree is any kind of a tree that connects all the different vertices together and does not have any cycles. And so what I mean by that is that there is exactly one path from each vertice to another vertice in that spanning tree, and there's no cycles. So there is no multiple paths to get from one vertice to another. There's only one path to get from one vertice to another. And it includes all of the vertices in G. That's a spanning tree. A minimum spanning tree is taking all of the possible spanning trees and finding the one that has the lowest total weight. So if you add up all the edges in your spanning tree, and you're trying to get that as low as possible to get the minimum spanning tree. Now, distinct minimum spanning tree, these are a lot of keywords. Distinct minimum spanning trees. You can have multiple minimum spanning trees as long as all of your minimum spanning trees have the same lowest possible weight. So you could have in a certain graph more than one minimum spanning tree, in that you have more than one way that you can connect up all the vertices without creating cycles, as long as all the possible ways have the same total lowest weight. So we're going to talk about that question in a second. I'm actually going to skip over that question for now because we're going to find that it kind of crosses over with some of these other ones. The second question that we have here is, if Prim's algorithm is run on G starting at vertex 1, the weight of the first edge added to the minimum spanning tree is blank. Now, remind yourself, Prim's algorithm is an algorithm for finding the minimum spanning tree of a graph. And so this is why I said we should skip one, because we are actually going to find the distinct minimum spanning trees of G and know how many of them if we run Prim's algorithm. So let's just go ahead and run Prim's algorithm, and that way we can knock out both 2 and 1 in the same go. So Prim's algorithm, remind yourself how that works. Prim's algorithm has a few different steps to it. The first step is that let me write this down, algorithm has, the first step is that we select a starting vertex. Select start. In this case, it tells us what it wants our starting vertex to be. It'll be 1 in this. I want to clarify that you don't need that. The starting vertex does not need to be something in particular. It's an arbitrary note. Usually the question will tell you which one it wants to be your starting vertex to, because it can change what the answer is. The second step is that we are going to look at all of the edges that cause our current minimum spanning tree to add a edge that is to add a vertice that is currently unadded to our minimum spanning tree. So look for, I'm going to clarify this part in a second, but minimum addition to MST. Let me highlight. I'm going to show you what edges are currently in our minimum spanning tree as we go. I don't want to lose this though, so I'm going to copy our tree here. We can paste it down here. There we go. I just want to be able to draw it over the original and not have to rewrite it. So we've got, we have our starting vertice that it tells us that our starting vertice is 1. So 1 is included in the MST right now. 1 is the only vertice that's currently included in the MST. So Prim's algorithm, the second step, tells us to look for the minimum addition to the MST. So we know that the vertice 2, 3, 4, and 5 are not currently in the MST, but need to be in there by the end of this. So what are the edges that we could add that are connected to our current MST of 1? What are the edges that we could add that would allow us to connect it with a currently unconnected vertice? Those edges are 1 to 2, 1 to 4, 1 to 5, and 1 to 3. All 4 of those edges will allow us to add in a new vertice that's not currently part of it, not currently part of the MST. And so the way that we want, the specific edge that we want to add out of those is the minimum edge out of those 4 options. And so because those 4 options, we have 4, 7, 5, and 6 are the weights, we know that the minimum one that we want is the edge from 1 to 2 of weight 4. So now we have our MST as of right now is just the edge from 1 to 2, including the vertices 1 and 2. The third step of Prim's algorithm is to do 2 again. That's it. That's the whole algorithm. It's super simple. We just go back to step 2 and we do it again until we get our full MST. So now we have our MST of 1 and 2, and we need to see what are the different edges that we could add to this MST to be able to add in a new vertice that's not currently in it. So the edges I see are, I write this in a different color, because these are not currently added to our MST, but these are what we're considering to add. 1 to 3, 1 to 5, 1 to 4, and 2 to 3. Those are the 4 different options that we have to add. These options have weight 6 for the 1 to 3, the 6, 5, 7, and 4. And so once again, we want to go with the lowest possible weight. And so we're going to pick the edge from 2 to 3 to be added to our MST. And so now we've added 3 into the MST with that edge 2 to 3. The next step is that we just do 2 again. So we're going to now look for edges that will add a new vertice into our mix, into our MST. And so those edges are going to be 1 to 5, 1 to 4, 3 to 4, and 3 to 5. The weights we have here are 5, 7, 3, and 6. The lowest of those being 3. So we go ahead and add the edge from 3 to 4 into our MST. And yeah, so now our MST has 1, 2, 3, and 4, but not yet 5. So for our last step, we have to consider all the edges that we can start to include that last number 5. So I see 1 to 5, 3 to 5, and 4 to 5 as all the possible options. Those have weight 4, 5, and 6. So once again, we go with the lowest option of 4. And so now we have our MST. Our MST includes the edge between 1 and 2, the edge between 2 and 3, the edge between 3 and 4, and the edge between 4 and 5. So let's go back to our question. Let's look at question 2 right now. If Prim's algorithm is run on G starting at vertex 1, which is what we did, the weight of the first edge added to the minimum spanning tree is blank. If you remember correctly, the first edge that we added was the edge between 1 and 2. And the weight of that edge was 4. So therefore, the answer to the question for number 2 is 4. Write that in the box. All right, let's go back to 1, because I told you that we were going to go back to 1 using this. So the question asked, G has blank distinct minimum spanning trees. If you are not familiar with distinct minimum spanning trees, this part might be a little bit confusing for you because this is not a very good example. In that there are no minimum spanning tree. There is only one distinct minimum spanning tree. There is no alternative minimum spanning trees in this example. And the reason for that is that if we would have had a scenario, like let's say at the very beginning, let's say that this edge was not 6. It was actually 4. At the very beginning, when we had the 1, and we were considering either adding this edge or this edge, we wouldn't have known whether to add the edge from 1 to 3 or the edge from 1 to 2, because both of those edges would have been the same weight. And so in that scenario, we now get a second alternative minimum spanning tree because of the fact, or we could get a second alternative minimum spanning tree. We have to continue Prim's algorithm through the rest and see if they end up being the same or different. But the point is that when you have duplicate values like that, in that you could take 2 different paths, but the algorithm doesn't necessarily say which one you should take, that's when you can have more than one distinct minimum spanning tree. But we don't have that in this scenario. In this scenario, we only have that one minimum spanning tree, and so therefore G has one distinct minimum spanning tree. That's the answer to 1. All right, I am going to minimize our algorithm for prims so that you can look back at that if you need to. And we're going to delete this because we have a copy down here. Fantastic, that worked. All right. Next question we have is if Kruskal's algorithm is run on G, the weight, sorry, I want to move this up a little bit further. The weight of the last edge added to the minimum spanning tree is blank. So Kruskal's algorithm, another algorithm to remind yourself of. Kruskal's is an algorithm that is also, it's essentially an alternative algorithm to Prim's. It also is aimed at trying to find a minimum spanning tree for a graph. They work similarly, but they can give you different results. So it is important to know the differences between the algorithms, but they will all give you all the possible minimum spanning trees of a graph. So Kruskal's algorithm has, again, 3 main steps. Kruskal's algorithm has 3 main steps. The first step, actually, I guess 4 main steps if we're including the first step from Prim's. First step is to select a start. That's basically what you do in almost every single graph algorithm. So in this case, it I completely said that wrong. Kruskal's is actually one of the few algorithms that doesn't have you select a start. That was a trick question. You don't you don't need to have a starting vertex in Kruskals. I apologize. The first step of Kruskals actually is to sort the edges in let's write down what the official terminology, non-decreasing. I hate this terminology because it's just like, it's basically increasing, but you're just putting fancy words on it. Sort all the edges in non-decreasing order of weight. Apologize for my poor handwriting. I'm struggling to get it in this small area. I'm trying to minimize this a little bit. So we are supposed to sort all of the edges in non-decreasing order weight. In other words, we're basically taking all of the edges that we have here in this edge list at the top, and we are going to try to sort them in order of weight value. So the lowest weight that I see here is 3, 4, 3. The second lowest that I see is the weight 4. So there's a couple different ones we have here. We have 1, 2, 4. We have 2, 3, 4. And we have 4, 5, 4. Next, we have the weight 5, which only is associated with the edge from 1 to 5. So 1, 5, 5. Running out of room. We have for weight 6, we have 3, 5, 6. And for weight 7, our last edge is 1, 4. Oh, sorry, there's actually 2, 6 weight edges, 1, 3, 6 as well. The order that you place these in within this list is arbitrary. That is what will cause you to get distinct minimum spanning, more than one distinct minimum spanning tree for this algorithm. So don't worry too much about the order. We already know, because we looked at this with Prim's algorithm, that there is only one distinct minimum spanning tree. So we know that the order isn't going to affect our final result. Last one is 1, 4, 7. Okay, so that is the order of edges. That's our first step for Kruskals. Second step is to pick the smallest and check for cycle. Okay, so this one's going to require a little bit of explaining. So the whole idea with Kruskal's algorithm is that we are going to look through, we're going to find the lowest edge that we have not looked at yet, and we're going to try to add it to our MST, and we're going to see if it has created any cycles. If you'll remember, minimum spanning trees don't have cycles. So we want to add all of the lowest possible weight edges that don't create a cycle. So let's go ahead and do that, and maybe that'll make more sense as we go. So the first one that we're looking at is 3, 4, 3. That's our lowest weight edge. And so we're going to add the edge between 3 and 4 and see if it creates any cycles in our MST. Because our MST is just right now 3 to 4, there is no cycles because it's just literally one edge. So it can't have a cycle. So that is our second step of Kruskals. Third step is to, you guessed it, repeat until there's a couple different ways you can decide when you end. You could say repeat until you've got an MST, the fact that repeat until you've spanned across all the vertices, or usually the easier one for computers to see is that repeat until you have v minus 1 edges, where v is the number of vertices that you have. If you have v vertices, a minimum spanning tree will always have v minus 1 edges because of the fact that you need one edge between. It works out. I'm not going to explain that right now. Point is, we're going to go back to step 2, and we're going to pick the next smallest edge. Next smallest edge being 1, 2, 4. As I've said, remember the order doesn't matter for the ones that have the same edge. It's for ones that have the same weight. So we're going to go ahead and see if we can add in the edge 1, 2, 2 of weight 4. Now you'll notice that this edge doesn't connect to our previous edge, and that's okay. In Prim's algorithm, we're only adding on the edges that built onto our current MST, that didn't create cycles and built on from where we were. In Kruskal's algorithm, we don't necessarily care about building up our minimum spanning tree from where it currently is. We kind of just let them all form around the graph, and then they'll connect together as they go. So the next edge we're going to look at is 2, 3, 4. We add 2, 2, 3 into the MST, and then we look at this and we say, have we created a cycle? Is there a way that we can get from one vertice in the MST to another vertice in the MST? Is there more than one way to get from one vertice to another vertice in the MST? No, right? Because we've just got the path 1 to 2, 2 to 3, 3 to 4. There is no cycle in that. There is no way to reconnect to another vertice. So we're good so far. Next, we have 4, 5, 4. So we are going to add the edge from 5 to 4. And we are once again going to check, does this create a cycle? No, it doesn't. Because of the fact that we don't have any second path to get from one vertex to another. So for example, to convince yourself of that, look at vertex 5 and look at vertex 1. How do you get from vertex 5 to 1 in our MST? Currently, the only way is 5 to 4, 4 to 3, 3 to 2, 2 to 1. There is no other path to get from 5 to 1 in this blue MST that we've drawn out. Awesome. So now, at this point, we have 1, 2. Let's put these. We have 1, 2, 3, and 4 edges in our system that has gotten to our v-1 edges requirement, and so we're done. This is the MST that we found from Kruskal's. I did not keep the other one. I should have, but point is that this MST, if you'll remember, was the exact same MST that we got when we used Prim's algorithm. So once again, that confirms that we did this correctly. Gonna make this smaller, and then we can actually answer the question that it gives us here. The question was, if Kruskal's algorithm is run on G, the weight of the last edge added to the minimum spanning tree is blank. So this is it's the question that might confuse people a little bit, because if you remember, I said that the order didn't entirely matter when it comes to these to these three, because they all have the same weight. And so we could have had 4, 5, 4 over here and 1, 2, 4 over here, and that would have switched which was the last edge that we added. And you're correct with that. However, the question says, what is the weight of the last edge added to the minimum spanning tree? And so we know that the last edge that we added was this. It could have been this, or it could have been this, but the point in it is, in all cases, that the weight of the last edge added to the minimum spanning tree, regardless of how you order it, is weight 4. Beautiful. All right, let's prepare ourselves for the next question. Next question that we have is, if Dijkstra's algorithm is run on G, if Dijkstra's algorithm is run on G, starting at vertex 4, the weight of the third edge added to the shortest path tree is blank. Once again, this question has given us a third algorithm to look at. I really hope that if you're watching this, the current professor of CS251 allows you to have a cheat sheet where you can write down the algorithms, because there's a lot of things to remember. I will be so honest. I am currently looking at another screen which explains the algorithm to remind myself of how these work. So don't feel bad if you're having trouble remembering how all these work. Dijkstra's algorithm is not a minimum spanning tree algorithm. this the other two that we've gone through so far were Dijkstra's algorithm is the algorithm to find the shortest path tree. The shortest path tree is a tree starting from some vertex such that you can get to every other vertex in the graph using the shortest possible distance. In other words, if you're we're going to be starting this at 4. That's not what I wanted. At 4, and so we're going to be starting from right here. The shortest path tree includes all the edges that are that allow us to get from 4 to 5, from 4 to 1, from 4 to 2, and from 4 to 3 in the shortest possible distance. Note that the shortest path tree may seem like it would be the same thing as the minimum spanning tree. It's not. And the reason for that is that we are optimizing it to try to make it so that all vertices are as close as possible to 4 in this tree. Whereas in the minimum spanning tree, we just wanted the total weight altogether to be as short as possible. So in the minimum spanning tree, we're trying to optimize the weight of the entire graph at once. In the shortest path tree, we're trying to optimize the weight of the path to 4 specifically. So the Dijkstra's algorithm is, I would say, a little bit more complex than the other two, but it's still definitely manageable. The Dijkstra's algorithm has a couple different steps to it, but I'm not going to go through the steps of the algorithm yet. We can talk about that in a second. I'm going to show you more of a graphical way to approach it, because I think it can get a little bit confusing if you're looking at the steps themselves. So essentially what Dijkstra's algorithm does is it creates a table. It creates a table with one value for each of the vertices in the graph. 1 through 5. In this table, each vertex is associated with a distance. And this distance is the current, the lowest distance that the algorithm believes we can get to 4. And so at the beginning of the algorithm, we're going to go ahead and set all of the non-4 vertices to infinity and the 4 vertices to 0. And what this means is that it will take an infinite distance to get from 4 to 5, from 4 to 3, from 4 to 2, and from 4 to 1. But obviously, from going from 4 to 4 is just, it's already on top of itself, so it's 0, is the distance from 4 to 4. And so essentially what we're going to do is we're going to explore all of the possible edges and see which edges we can use to make the distance from 4 to that vertice lower than it was before. I'm going to go ahead and start doing it, and I think it'll make more sense as we go. So we're starting at vertex 4, and the way that we want to work with this algorithm is that we start with the we're essentially going, the internal setup of Dijkstra's algorithm is set as a stack, and so we're going to be adding 4 to the stack. And what that means is that we are processing it's a min priority stack. We are processing the I'm saying this all wrong. I'm sorry. It's a min priority queue that we're using to hold this. We are going to be processing the smallest distance unvisited vertice first. So essentially what that means is that we're going to look at this table that we have here. We're going to look at the 1, 2, 3, 4, and 5, and we're going to see, out of these vertices, out of the ones that we haven't yet visited, which we haven't visited any of them yet, out of the ones that we haven't yet visited, which has the lowest distance to 4. The vertice that has the lowest distance to 4 is 4, because it has distance 0. So we're going to go ahead and visit vertex 4. I'm going to put a check mark to show that we visited it. And when we visit vertex 4, we're going to look at all of the edges that 4 has to other vertices. Hey, this is Boiler Exams Person here. I made a mistake in this part of the video, but this video took me an hour to record, so I'm just going to go ahead and insert the edit here. When we are looking at the edges for a vertice that we're visiting, you need to specifically look at those edges in the order of their weight. So in a second, we'll be looking at the edge between 4 and 3, the edge between 4 and 5, and the edge between 4 and 1. You need to look at them in that order specifically so that you are visiting the edge of weight 3, and then the edge of weight 4, and then the edge of weight 7. The order of those added does matter to this question in particular. Again, I made that mistake with all of the vertices that we're visiting in this algorithm, so make sure that when you're visiting the edges, when you're visiting the vertices for the rest of this algorithm, that you're visiting the edges of that vertice in the order of their weight. Thank you. We're going to look at the edge that 4 has to 3. We're going to look at the edge that 4 has to 5. And we're going to look at the edge that 4 has to 1. We're going to explore all of these vertices, and we're going to say, does this edge help us to get a shortest path tree, or does it not? So let's first look at the edge from 4 to 3. The edge from 4 to 3 has distance 3. So in other words, we know that we can get from 4 to 3 with distance 3. And we want to ask ourselves, is that less than or greater than the current value of the table? Like, is that less than what we previously believed was the distance to get to 3? It is. So the way that we write that down is that we then change the distance in our table from 4 to 3 being infinity to from 4 to 3 being distance 3. And we're then going to say that in our shortest path tree, you can go from 4 to 3 as a possible shortest path edge. I'm actually not going to include that. You'll see that as part of the algorithm, but I don't think that's necessary for visualizing it. Never mind. Ignore what I said. So we explored the edge from 4 to 3. Next, we have to explore the edge from 4 to 5. This edge right here. The edge from 4 to 5 has weight 4, and so we know that we can get from the point from vertice 4 to vertice 5 with distance 4. So in other words, is 4 less than infinity? Yes. Yes, it is. And so we correct our edge of our distance for 5 to be 4. Next, we look at the edge from 1 to 7. From 1 to 4. That has weight 7. Once again, we say, is 7 less than infinity? Is the distance between 4 and 1 that we have here less than what we previously thought it would take to get to 1? Yes, it is. It's less than infinity. So we can write down the weight 7 and keep that 1 for edge in our shortest path tree. Now we have visited 4, we have not visited any of their vertices. So we want to visit a new vertice in our set. We want to look at what is the vertice that has the shortest distance from 4. That's going to be 3. So we're going to now visit 3. Wrong color. We're going to visit 3. And we're going to, again, look at all the different edges that went between 3 and the other vertices. I see 1 to 3, I see 3 to 5, and I see 3 to 2. We're going to explore all those. I'm going to go through them one at a time. Now, first, let's look at 1 to 3. 1 to 3 has weight 6. And so we're going to do the exact same thing as we did last time, and that we're going to compare the new distance that we have to the old distance that 1 had. In that we know that we can connect, we already knew that we could connect 1 to 4 to 1 with weight 7, as the table says here. But now we are given a new option. We could go from 1 to 3 and have weight 6. And so the question is the path through 3 and then 3 to 1 less than the path between 1 and 4? And the way that the algorithm does that is it adds the distance to 3. Oh, shoot. It adds the distance to 3 to the weight of the new edge that we're considering. And then it compares that to the current distance between 1 and 4 already in our table. So in other words, is 6 plus 3 greater than or less than 7? 6 plus 3 is greater than 7, and so we know that this new edge between 1 and 3 would not help our shortest path tree to be any shorter. So in actuality, we don't want to add this edge to the system. Does that make sense? I'm going to say it one more time, because I think that this is probably the most confusing part about the Dijkstra algorithm. We add the distance that we know that it takes to get to 3 to the weight of the edge between 3 and 1, and then we say, is the sum of those two numbers a better and shorter path to 4 than 1 already had? Or is it worse than what we already had set up for 1? Because 9 is greater than 7, we know that this path from between 1 and 4 is better. So we are not going to add this edge 1 to 3 into our system. Another edge that we have here, and you'll get another chance to explore that same situation. Another edge that we have here that we haven't yet explored is 3 to 5. 3 to 5 has weight 6. And so once again, we have almost the exact same scenario in that we previously had an edge to 5 between 4 and 5. According to the table, we had a distance 4. And so we're comparing 6 plus 3 to what the current value was in the table of 4. The current value of 4 is less than 6 plus 3. 4 is less than 9. And so the previous edge that we had there is better than adding this edge in. So we're not going to add that edge. Lastly, we have the edge between 3 and 2. The edge between 3 and 2 is of weight 4. And so we're going to say 4 plus 3 less than the current distance to 2? And if we check the table, the current distance to 2 is infinity. So is 3 plus 4, which is 7, is 7 less than infinity? Yeah, it is. So we once again have a situation where we delete the infinity distance, and we're going to replace it with 7 now. And so we are going to go ahead and add this edge 3 to 2 into the system. And replace the distance to 2 with 7. All right. We're going to keep going. So we then go to the next closest unvisited vertice. If we look at our table, the other unvisited vertices are vertice 1 with distance 7, vertice 2 with distance 7, and vertice 5 with distance 4. So we can go ahead and go to vertice 5 and visit that one. Vertice 5 has 2 edges that are unexplored that don't include the edge that we already have in the system. We don't need to look at this edge because we already have it here in the system. But we have 1 to 5 and we have 5 to 6 that we have to explore. Sorry, we have 1 to 5 and we have 5 to 3 that we have to explore. First, let's look at 3 to 5. This is of weight 6, and so what we are looking at here is we're trying to see, is the previous distance that it took to get to 3 better or worse than the distance we would get if we took a path through 5? So is 4 plus 6 more than or less than the current distance to get to 3 of 3? Is 10 less than or greater than 3? 10 is greater than 3, so this edge is unneeded. We already have a better path for 3. Now we're going to consider 1 to 5. 1 to 5 is of weight 5. So we consider is the total between the weight of the edge and the current distance of 5. So is 4 plus 5 greater than or less than the current distance of 1 to 4, which is 7. Is 9 greater than or less than 7? 9 is greater than 7, so adding this edge does not help our shortest path tree. So we don't add the edge. All right. So now we just have 2 more unvisited vertices to look at. We have 1 and we have 2. It doesn't matter which one we look at first. They both have the same distance. So we're going to go ahead and look at 1 first. 1 has 3 different edges that we don't currently have in the system, so or in the shortest path tree, so we're going to explore those 3. 1 to 3 has weight 6. The question is the distance to 3 is the distance to 3 less than or greater than the distance to 1 plus the weight of this edge? The distance to 1 is 7. The distance to 3 is 3. The weight of the edge is 6. So 7 plus 6, because that's greater than 3, we know that this edge is unneeded. There is already a better path for 3. So we don't add that edge. Then we look at 1 to 5. Is the distance of 1 plus the weight of the edge that we're adding better than or less than the distance of 5? The distance of 1 is 7, the distance of 5 is 4, and the weight is 5. So is 7 plus 5 greater than or less than 4? 7 plus 5 is greater than 4. So this edge should be, this edge should not be added to the system. It doesn't help. Lastly, we have the edge between 1 and 2. The edge has weight 4. And so what we're looking at is the current distance to 2 greater than or less than the distance to 1 plus the edge of the weight of the edge? So the distance to 1 is 7. We add that to the weight of the edge. So is 11 greater than or less than the distance to 2 of 7? The current distance to 2 of 7, which takes this path from 4 to 3 to 2. 7 is less than 11, so we don't need this path. We don't need that edge right there. There's one more vertex to visit. We are almost done. We need to visit 2. The only path that 2 has yet to consider is the edge between 2 and 1. The edge between 2 and 1 has weight 4. 2's current distance from the 4 is, according to the table, is 7. So 7 plus 4 is 7 plus 4 less than or greater than the current distance for 1, which is 7. 7 plus 4 is greater than 7. 7 plus 4 is greater than 7. So we don't need to add this edge right here. Therefore, we have visited all of our vertices now. This is our shortest path tree. The question specifically asks, if Dijkstra is run on a G starting at vertex 4, the weight of the third edge added to the shortest path tree is blank. Now, ladies and gentlemen, what was the third edge that we added to the system? It's a great question. And if memory serves correct, okay, yeah, sorry. The third edge that we added was 7. Was the 1 to 4. One thing I do want to clarify that is actually super important to this specific question that I don't think I said explicitly. When you are looking, I definitely should have said this earlier. When you're looking at the different paths that you can explore when you visit a vertice, you should do it in the order of their weight. I apologize for not saying that earlier. That's an important step. I don't know if I did that for all of these visited vertices, but we know specifically for this initial one that we visited, we should be visiting this, this, and then this. So we should visit the 7 weight last. So in other words, the weight of the third edge added to shortest path tree is 7. Ladies and gentlemen, CS251 is difficult. I know it is. You guys got this. It's a hard class, but I believe in you all. All right. One last part to this question. Holy crap. I don't know how long this video has been going on for, but it feels like it's been an hour. The weight of any minimum spanning tree G is blank. Now, we made our minimum spanning tree before, and if you scroll back in the video, you can probably find exactly what the minimum spanning tree was. So I'm going to try to remind myself what the minimum spanning tree was that we found. Remember, this is the tree that we found when we ran Prim's algorithm and Kruskal's algorithm. The tree that we got, I believe, we'll draw it out as we go. The minimum spanning tree that we had included the edge of weight 3 and all of the edges of weight 4. This was our minimum spanning tree. So the weight of any minimum spanning tree of G is the sum of the edges of the in our minimum spanning tree. So in other words, we have edge weight 3 plus 4 plus 4 plus 4. That's all of the edges that we have in that MST, and that is 11. So the weight of any minimum spanning tree of G is 11. Ladies and gentlemen, question 4. Thanks for sticking with me. Hello everyone, so today we're looking at question 5. This question, I think, is a bit more fun. It's got to do with topological sorts, but there is a trick to it. And so we're going to talk about the trick, we're going to talk about the question, and hopefully get a better understanding of this. So question 5 states, let G be a graph represented by the edge list below. G is directed and unweighted. Before we go any further, I just want to clarify what directed and unweighted means. G is directed means that for every edge in G, there is a start point and an end point. You might remember from question 4 on this exact same exam, the edges were undirected, and so that meant that you could go from U to V, or you could go from V to U for each edge. But if it is directed, that means that you can only go from starting vertex U to ending vertex V. The other thing it gives us is that the graph is unweighted, and that basically just means that every single edge in the graph does not have a weight or a cost associated with it. So we're not going to be doing any algorithms like Dijkstra's or Prim's or Krusarju's that require us to have a weight for each of the edges. We're just going to say that all of the edges essentially have the same cost. There is no particular weight or cost associated with them. So it then gives us a set of tuples to represent an edge list. We're going to look at that in a second. And it asked us to show all the topological sorts for G. So topological sorts are a way of ordering the vertices of a graph in a way that all edges of the graph point from a earlier vertice in the order to a later vertice in the order. I'm going to show an example of what one of these sorts would be so that we can try to get a better understanding of this, because it is a bit of a complicated definition. So we're going to look at each of the edge pairs, each of the edges here, and we're going to try to figure out what those represent in the graph. So the first edge pair that we have says it goes from 2 to 3, and so that implies that there is a vertice 2 and a vertice 3, and then an edge goes from 2 to 3. Next one is there is an edge 3, 1, which implies that we go from vertice 3 to vertice 1 in that direction. Next we have 4 to 0. Both of these are not vertices we've seen before, so we will make them new. We go from 4 to 0. Next we have 4 to 1. We have 5 to 2. 5 is something we have not seen before, so we draw that in. 5 to 2. And then lastly, we have 5 to 0. So, a topological sort for G is essentially a sort in an ordering of these vertices that keep all of the edges going forward. So specifically, one possible sorting of this could be the sorting 5, 4, let's go with 2, 3, 0, 1. And the way that we verify that this is a topological sort is that we add the edges that we've seen in this graph back into the sort. And so we're going to write all the edges, and what we want is for all the edges for a topological sort to go in this direction. There should be no edges that go backwards. So let's write in these edges. We've got the edge 2 to 3 that it gives us. We've got the edge 3 to 1. We've got the edge 4 to 0. We've got the edge 4 to 1. By the way, I'm taking all these edges from the edge list up here. That's what I'm reading off of. We've got the edge 5 to 2. And we've got the edge 5 to 0. Now, we look at all of these edges, and we are essentially to verify that it's a topological sort, we just need to know, do all of these edges go forwards? Are there any edges that go from left to right? All of the edges that we see should be going are there any edges that go from right to left? That's bad in the topological sort. For a topological sort, we want all the edges to be going from left to right. So this is a completely valid topological sort because of the fact that all arrows are going to the right. Now, the difficult part about topological sorts is not finding one that works. The difficult part is finding all of them that work, because this question asks you to show all topological sorts for G. And so there's a trick to doing that, and I'm going to show you that trick. The trick to doing that essentially has us use a kind of algorithmic method. And what we're going to do, actually, I don't want to get rid of that. I'm going to minimize that and put it to the side in case you want to look at that later. This is an example of a topological sort. So the trick to the topological sorting algorithm is that we want to look at the first step is to look at all of the vertices that have 0 out degrees. Sorry, that have 0 in degrees. We look at all 0 out degree vertices. And remind yourself, an out degree is the number of edges that are leaving a particular vertice. I said that backwards. I kept getting them confused back and forth. We need to look at all of the 0 in degree vertices. Sorry. You can do it both ways. It doesn't totally matter which way you do it, but there's a certain you'll get the topological order backwards or forwards depending on which direction you do it. But let's for this instance look at all 0 in degree vertices. So what that means is that in degrees is the number of vertices that are going into a particular vertice. There are a number of edges that are going into a particular vertice. So we are going to look at all the 0 in degree vertices. So in this particular graph, we want to look at the in degrees of each of the vertices. So looking at 4, we see that we have 2 edges going out of 4, no edges going in. So the number of in degrees of 4 is 0. Looking at 2, we have an edge going in and an edge going out, so the in degree is 1. Looking at 3, we have an edge going in and an edge going out, so the in degrees is 1. Looking at 1, we have 2 edges coming in, but none going out, so the in degree is 2. Looking at 5, we have 2 edges going out, but none coming in, so the in degree is 0. And looking at 0, we have 2 edges coming in and none going out, so the in degree is 2. So we want to look at all of the 0 in degree vertices, and we want to, step 2 is to pick one and remove its edges. Step 3 is going to be repeat. Make this a little bit smaller. So, don't know what happened to my stuff here. Degree vertices. Yeah. So we can either pick, if you remember correctly, we said that 4 and 5 both had 0 in degrees. And so we can either pick to remove 5 or 4 from this graph. And so picking one of them, 5 versus 4, or picking the other is going to be what's going to cause us to have multiple different topological orders. For this first one, we're just going to go through one topological order with this algorithm, and then I'll show you how you can keep track of all of them at once. So let's say that we remove vertice 5 from this topological from this graph. We remove 5, and step 2 says to remove all edges associated with it. So we are going to write down that we removed 5, and then we're going to remove all of the edges, and then we're going to repeat. We're going to go back to step 1. We're going to now look at all of the vertices. We see 1 has in degree 0, 3 still has in degree 1, 1 has in degree 2, 0 has in degree 1, and 4 has in degree 0. So once again, we can now choose which vertice do we want to remove from this. We either have the options of removing 2 or the option of removing 4, because both of these have 0 in degrees. Let's just go ahead and remove 2 this time, because that way we get a different one than our example. So if we remove 2, we remove 2 and we remove its edges, and we write down 2 in our listing. Now we look at it again. We're at step 3. We go back to the first step and repeat. We look at 3 has 0 in degree vertices, 1 still has 2, 0 still has 1, and 4 has 0. Let's remove 3 this time. We can remove 3 and its edges. We write down 3 in our ordering, and we are left with two more, with one vertice that has 0 in degrees and 2 vertices that have 1 in degree. So at this point, our only option is to remove 4. We remove 4 and all of its edges. Write it down. And now we can either remove 0 or we can remove 1. Either of these can be done in either order because they both have 0 in degrees. Let's just say that we remove 1, and then after that we can remove 0. This is another topological sort that we've just come up with. And so you can essentially do this method and backtrack yourself through to see all the different times that we could choose between 1 or 2 vertices to remove. That's where you're going to get your different types of topological sorts. But it can be really hard to keep track of that. And so what we're going to do instead is I'm going to show you a method that we can essentially do that same thing that we've got so far. We're going to use the same algorithm, but we're going to create a tree as we go. And that tree is going to allow us to keep track of which options that we have at each point. So we're going back to the very first scenario. We've got 5 and we've got 4 that we can remove in this first scenario because both of those have 0 in degrees. And so we are going to make a tree where 5 and 4 are our top 2. And sorry, I said this is a tree. It's not totally a tree because it's kind of 2 trees. I guess we could actually say it's 1 tree and just put like this vertex tree node at the top that says start. So for the start, we could either remove 5 or we could remove 4. Now let's just look at 5. Let's ignore 4 for now. Looking at 5, if we removed 5, we imagine that we took out this stuff. What options would we have? I wish I wouldn't have removed all this, put all this down. What options would we have to to add to this listing next. I want to copy this down so I can write on it. What options would we have next if we removed these edges and 5? We could then either remove 2 or we could remove 4 next. And so what we're going to do to show that in the tree is that we're going to write 2 nodes coming out of 5. We can remove 4 or we can remove 2. Let's go down this path, and of 4, let's say that we remove 4 from this. We can now remove either 0, because 0 has 0 in degrees now, or we could remove 2. These 2 vertices still have 1 in degree. So we can remove 0 or 2, so we write them both down in our list. 0 or 2. Move this out of the way. Let's say that we removed 0 from that. Then we would only have one other option that we have, which is to remove 2. So under our 0, we're going to write that we just have one option of 2. After we remove 2, hopefully it's fairly easy to see that we would have to remove 3. We have to move 3 next, and then we would remove 1. 1 would be our last vertex in there. So we have 2, 3, 1. So let's backtrack now. Let's look at the scenario in which we removed, delete this and get us a fresh one going. Let's look at the scenario in which we went along this path, so we went 5, 4, and then we went 2. Actually, I'm going to write real quick to just help us keep track. At the bottom of our tree after the 1, we're going to, this is a 1 down here. We're going to say end, because that was, we'll say E for end, because that was the last vertex that we needed to remove. It's just to help us keep track of which paths down our tree are finished, and we don't need to look at them any further. So instead, let's go back to this. We removed 5, we removed 4, and we removed 2. Let's get rid of those in our graph. Once again, copy this. When you are doing this yourself, you don't need to draw the graph. If you draw the graph and draw what you remove every time. If you think you can get it in your head and that you can just see it, that's totally okay. But I want to draw it out for these first couple ones so everybody can understand what I'm doing. So let's say that we removed 5. Removed 5. We removed what? We're doing 5, 4. And what we say 2. Don't like when it does that. So that means that we have the options 3 has 0 in degrees and 0 has 0 in degrees. So we can then say under that 2, we either have 3, it's way too big, 3 or 0. If we removed the 3, then we could either do 1 or 0 as our next one. And regardless of which one we do, we would have to do the other one as our last vertex. I write way too big. If we were to go back to here and say we remove 5, 4, 2, and 0, then we would have to remove 3 and 1 in that order next. 3, 1, and all of these are our last vertices, so we can go ahead and write the end symbol to let us verify that. Okay, this is for, so we have now found 4 topological sorts, and I'm going to show this to you, specifically what this tree is saying. This tree that we've made so far is saying that there's a topological sort 5, 4, 0, 2, 3, 1. There's a topological sort 5, 4, 2, 3, 1, 0. There's a topological sort 5, 4, 2, 3, 0, 1. And there's a topological sort 5, 4, 2, 0, 3, 1. Now, we're going to continue to fill up this entire tree and fill it out completely so that we look at every single possible topological ordering. Only then can we say that we have found all of the topological orderings, and we need to write those down to answer the question, to show the topological sorts for G. This question is a bit long in that respect, in that it's difficult to find all of the topological sorts, but if you use this tree method to keep it organized, you'll do it. You'll make sure that you don't miss any important ones. All right, we are going to keep going. I can erase all this. I can delete. All right, let's go back. So we've got start 5, 2 that we have not yet explored. So let's say that we remove 5, we remove 2, and now what are the options that we have next to remove? We could remove 3, or we could remove 4, because both of those have 0 in degrees. 3 or 4. If we were to remove the 3, we could remove 4 only, because 1 and 0 still have 1 in degree at that point. So we have to remove the 4 next in that ordering. After we remove the 4, we could either remove 1 or we could remove 0, and in the other option we would remove just the opposing one that we haven't removed yet. So 0, 1, 1, 0. And these are the last of their kind, so we'll do the E note at the end. Backtracking, we've got the one where we went 5, 2, 4. So let's draw that part out. 5, 2 are already crossed out in this current graph. Then we're just going to cross out 4 instead. The options then that we have is 3, which has 0 in degrees, and 0, which has 0 in degrees. 1 still has 1 in degree, so we can only remove 3 and 0 from this one. Removing those, 0 or 3. If we were to remove 3, then we could remove 1 or 0. And once again, as in several of these other examples, we then have to remove the opposite of the one that we removed. If we went back and we removed, after we removed 5 and 2, if we moved 5 and 2 and 4 and 0, we then could remove 3, and then we would have to remove 1 after that, in that specific order, because only the 3 after 0 has 0 in degrees. As you can see, these topological sorts can get very complicated quickly, and so that's why it's important to keep it organized like this. Now, when you have a topological sort like this, we have now completed half of the topological tree, in that we have done the 5 verses instead of doing the 2. We can do the same method of crossing out across the graph as we go to do all the 1s and the 4, but as we've seen, this takes a good amount of time, and so you can kind of, after you've done enough of these sorts, you can kind of see what would need to come next in the order. And so we're going to use that path instead, in saying that we don't need to necessarily cross them out as we go, but we'll instead just kind of remember in our head. We'll definitely look at the graph, but we will not cross things out, as to not make this video take longer than it needs to, because I'm guessing that you guys have the whole hang of this by now. And if you haven't, go back and watch the first part of the video of where we're doing these topological sorts for the first time, and hopefully it'll start to make more sense. All right, so if we were moved to remove 4, the options I see are are 5 to remove after 4. If you remove 5, because 5 is the only one with 0 out degrees at that point, because 0 and 1 have not been freed up. Now, actually, something that I see that I see in this scenario that could help us to fast track our tree that we're making is that in this branch right here, we removed 5 and then we removed 4, and then we looked at the things that had 0 out degrees from that point on. But the truth is that if you remove 4 and then 5 versus 5 and then 4, you'll still get the same number of out degrees. Of in degrees in each of the vertices. So what we actually can say from that is that this whole tree part right here should be exactly the same as what we have over here. And that helps us to make this whole thing a lot easier, because then we can we can skip over doing that whole set again. And so what we get in this scenario is a series of orderings, and we need to write those all out to fulfill the question. Real quick, I am going to count the number of orderings that we have to make sure that I did this correctly, because I have the number that we're supposed to have down written here. So we've got 1 ordering, 2 orderings, 3 orderings, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we just need to now write down the orderings that we had here in this tree. The orderings according to the tree were 5, 4, 0, 2, 3, 1, 5, 4, 2, 3, 1, 0, 5, 4, 2, 3, 1, 0. We have 5, 4, 2, 3, 0, 1, 5, 4, 2, 0, 3, 1. All of these orderings that I'm looking at them as I'm just going down this tree one at a time. So the first one was 5, 4, 0, 2, 3, 1 correlates with 5, 4, 0, 2, 3, 1. That's where I'm getting this order from. So I'm not going to write down the whole order, because we have it up in the solution on the boiler exams page. But essentially, you want to draw out this tree and then verify that you are hitting all of the orderings that we have here. For the actual answer, you're going to want to write these all out. But we have it here, so go off of this. Hello everyone, today we're looking at question 6 on the exam. So this question is, it's short and sweet, and I've got a love-hate relationship with these kind of questions, because it will require you to think, and so it's going to be difficult from that aspect, but it's not going to require you to do any long algorithms like we've had to do for several of the questions on this exam. So the question states, what is the minimum number of edges that you would need to add to the graph below to make it strongly connected? Briefly explain your reasoning, blah, 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 and then it gives us a graph. So the first thing we need to cover real quick is, what is a strongly connected graph? A strongly connected graph is a graph where every vertice can reach every other vertice within that graph. The thing to keep in mind is that for strongly connected, usually it's a concept that's associated with directed graphs, because the point is that, for example, in this graph, 3 is connected to 8, but 8 and 3 are not strongly connected because 8 has no way to go to 3. 3 can go to 8 by just traversing this edge, but there is no set of edges, there's no path in which 8, if you're starting at 8, that you could ever get to 3, because 3 has no edges that go into it. And so the goal of this question is to say, how many edges do we need to add so that we can pick any edge on this graph and get to any other edge on the graph? We could choose 9 and be able to get to 5, or we could choose 11 and be able to get to 3. How many edges do we need to add to make that possible? So There is one instinctive answer that I think several people go towards, and I put that as one of the false answers on the multiple choice section for this question because I'm evil. And so I'm going to show that example real quick, and then I'm going to show why that's not the best answer here. So one of the things that you'll initially notice when you look at this graph is that they ordered it nicely in that all of the vertices with 0 in degrees, or in other words, with no edges going into them, are at the top, and all the vertices at the bottom have no edges coming out of them, or 0 out degrees. And so what we know is that we need to make this strongly connected, we need to have edges on the bottom linking to edges on the top. Because if we do that, that will allow us to go from 9 to, like, if we had an edge from 9 to 7, that would allow 9 to get to all the things that 7 connects to. Like 9 could get to 2 by going 9, 7, 11, 2, or 9 could get to 10 by going 9, 7, 11, 10. All of those things are options. So we know that we need to be making edges that go from the bottom here to the top row here. And what I think several people are going to instinctually do is just say, okay, let's make it simple. Let's put an edge from 2 to 7, let's put an edge from 2 to 5, edge from 2 to 3, edge from 9 to 7, edge from 9 to 5, edge from 9 to 3, edge from 10 to 7, edge from 10 to 5, edge from 10 to 3. This is getting very convoluted very quickly. And you're correct. If you were to do this, send edges from the bottom to edges on the top, to vertices on the top, vertices on the bottom to vertices on the top, like this, this is strongly connected. This is absolutely a strongly connected graph now, because of the fact that we can now get from any vertice on this graph. You can verify that further for yourself. Look at any vertice on this graph. Can you get to any other vertice on the graph? Yes, that's true. The issue with this is not the most optimal way to place the edges so that we have the minimum number of edges to get to a strongly connected graph. The way that we get to a strongly connected graph with the minimum number of edges is that we want to have the minimum number of out degrees and in degrees added to these vertices. And we can accomplish that in a much simpler method by instead sending 2 to 7, 9 to 7, and 10 to 7, and then just sending 7 to 5 and 7 to 3. If we do this, now we can get from, say, 10 to 3 by going 10 to 7 to 3. We can get from 10 to 7 to 5. And so we can get to all of these top rows from any of these by instead just going through 7 as kind of a juncture. An alternative way you could look at doing this, and I'm just going to write down the number of edges that it took us to do this was 5, whereas the number of edges that it took us to do all 3 of these bottom vertices each to all 3 of the top vertices took 9, and that was incorrect. That's too many. We can also, if you wanted to, there's several different ways that you can draw the edges on this, and I'm just going to show another one real quick in case you made a different set of edges and want to make sure that yours is correct. As long as you get five edges and it's strongly connected, your answer is correct. But another way you could do this is you could send 2 to 9 and 10 to 9, and then send 9 to each of these. And again, we kind of use 9 as a juncture here, so that we can add the minimum number of edges in order to get this graph to be strongly connected. Once again, this is kind of a simple problem in that it doesn't take too much algorithmic wise. There's a ton of different answers that you could use, but the minimum number of edges that you need to add to the graph to make it strongly connected is 5. Today we're looking at question 7. Question 7 is not too tricky of a question, but it is not tricky after you understand what the question is asking. And if you don't understand what the question is asking, you'll get a totally different answer. And so the question itself starts out saying, let G star be the transitive closure of a simple digraph G. G star is represented by the following adjacency matrix. The first time that I looked through this question and I created the answers for boiler exams, I didn't read that first sentence at all. in my head, I was thinking G is represented by the following adjacency matrix. And so I didn't even take into account the transitive closure idea. And so you need to take into account the fact that it says that the G star is a transitive closure of a simple digraph G, because that changes the entire problem. So first of all, let's talk about real quick, what is a transitive closure of a graph? A transitive closure of a graph G, G star in this case, is a way of essentially looking at the reachability of each vertex of G to another vertex of G. In that if in G, sorry, not G star, if in G, U, the vertex U can reach B, and what I mean by that, let me make this look like a U. What I mean by that is that there is a path in this directed graph G that you can take to reach V. So either there's an edge right between U going to V, or there is an edge from U to X, and then an edge from X to V. Point is that there is some path of edges that you can take to reach V. If in G that is true, then in G star, there will be an edge UV. So let me reiterate that. If in G, the vertex U is able to reach the vertex V through some path, in G star, there will be an edge directly from the vertex U to the vertex V. So if we're specifically looking at this adjacency matrix, let's look at a couple of these values and try to explain what that means. So for instance, if we look at the row for 4 and the column for 2 in this G star adjacency matrix, essentially what that's saying is that there is an edge in G star from vertex 4 to vertex 2, because there's a 1 in that spot. If there's a 0 in that spot, it means there's no edge. If there's a 1 in the that spot in the adjacency matrix, it means there's an edge. And so because of the fact that there is an edge from 4 to 2 in G star, that means that in G, 2 is reachable by 4. If you start in 4, you can find a path to get to 2 in G. And so that means that in G star, we have an edge from 4 to 2. So let's use that to try to answer some of these questions. Move this up here. So the first question that we have is, G has at least one topological sort. We're supposed to answer this true or false and then explain it. So let's remind ourselves, what is a topological sort real quick? A topological sort is a way of ordering the vertices of a graph so that if we draw in all the edges, all of the edges will go from left to right. There will be no edges that go from right to left. So is there at least one way to sort the vertices of G so that that is true? This is probably not a super instinctive question for a lot of people, in that it's not necessarily obvious how you would use the transitive closure adjacency matrix to be able to prove that. But one of the things that I will tell you now with topological sorting is that if you think about it, if a graph, let's give an example, if a graph with a vertex A and a vertex B has a cycle, in that there is a edge from A to B, there's an edge from B to A. If that graph has a cycle, then it is impossible for that graph to have a topological sorting, because there is no way to order A and B so that you have all the edges going from the left to right. There is no way to order those vertices in that way. And so if you ever have a cycle in a matrix, like for in this case in matrix in a graph G, then you cannot have a topological sorting for that graph. So in other words, can we show that there is a cycle in graph G? And I believe we can. And so the way that we would see that is that we look at the reachability of a pair of vertices. So for example, this marking in the row 0, column 1 being 1 means that 0, that if we start at 0 in G, we can reach 1. It's saying that in G star there's an edge between from 0 to 1, and that if we start at 0 in the graph G, then we can reach 1. Now we can also look at the row 1, column 0, and because there's a 1 there, that means that there's an edge from 1 to 0 in G star, which means, on the opposite end, that we are able to reach 0 from 1 in G. So in other words, we can, for one, we can reach 1 from 0, and we can reach 0 from 1. Therefore, G has at least one cycle. So it cannot have a topological sort. Therefore, the answer to this first one is false. So because of the fact that we've found a cycle that exists within G, there is no way that it can have a topological sorting. We know that it can't even have that at least one. We'll throw this up here. All right, so the next question we have is the vertices of 0, 1, and 1, 4, and their associated edges between them in G represent a strongly connected component of G. So remind yourself what a strongly connected component is. A strongly connected component in a directed graph is a set of vertices that are all able to reach one another. In that, in this set of vertices 1, 0, 1, 4, in G, 0 should be able to reach 1, 0 should be able to reach 4, 1 should be able to reach 0, 1 should be able to reach 4, and 4 should be able to reach 0, and 4 should be able to reach 1. All of those three vertices should be able to take some path to reach one another. So this question, as opposed to the other one, doesn't necessarily take a lot of critical thinking, and that remember that this G star adjacency matrix up here tells us directly whether or not one vertex is able to reach another. In that, if we can find, if we look in row 0, we should be able to find that in column 1 and column 4, both of those are, both those have a 1 in those spots. In other words, meaning that 0 can reach 1 and can reach 4. And so we look in row 0, we look to column 1, and we see that 0 can in fact reach 1. We look in column 0, we look to row 0, column 4, we see that there's a 1 there, so 0 can in fact reach 4 in G. So let's keep going. 1 is able, we look in row 1, we look to column 0, and we see that 1 can in fact reach 0 because there's a 1 there, and 1 can in fact reach 4 because there's a 1 there. Again, we look to row 4, we look in column 0, and we see that 4 can in fact reach 1, and 4 can in fact, 4 can in fact reach 0, and 4 can in fact reach 1. So therefore, all three of these vertices are able to reach each other in G. So because they can all reach each of the other vertices, then this is a strongly connected component. So 2 is true because all three vertices can reach each other according to G star adjacency matrix. another way to say this would be that for each pair ij, where I is either 0, 1, or 4, and j is 0, 1, or 4, there exists an edge ij in G star. You can explain that however you want, but the point is that we verify that this point exists. That this point exists. This point is 1. This point is 1. This point is 1, and these 2 points are 1. All right, one last part to the question. I'm just going to put that over here. Last part to the question is part 3. It says the in degree of vertex 2 in G is 0. Now, so knowing the number of in degrees to a vertex in a graph when you're given the transitive closure adjacency matrix is a bit tough, in that you don't necessarily know what, if you're only given the transitive closure adjacency matrix, you don't know what the edges are that exist within G. You just know which vertexes are reachable by other vertices. And that can give you some information on the edges, but not a ton. However, this specific one is asking if the in degree of vertex 2 is 0. In other words, that's saying that there are no edges that go into 2. Because remember, the in degrees are the number of edges that go into a vertice. The out degrees are the number of edges that come out. And so this is saying the in degree of vertex 2 in G is 0. So there's no edges coming in other words. So if the number of in degrees in vertex 2 is 0, then logically we can reach the assumption that it is impossible to reach 2, right? Because if there is no edges going into 2, then no other vertice could ever reach 2. There is no way to get into 2. It's like having an airport that only has planes flying out, but there's no planes flying in. So how is anybody going to get in there? We'll ignore parking lots and things like that. So in other words, we should have, for all vertices in G star, there should be no edge from that vertice to 2, besides maybe 2 itself, because nothing should be able to reach 2. So let's look and see if that's the case. We look in row 0, and we see that in column 2, there is actually a 1 there. This is true for 1, 1, 2. This is true for 4, 2. It's even true for 3, 2. So we actually see that all of the other vertices are actually able to reach 2. So because any of them are able to reach 2, we know that the in degree of vertex 2 has to be at least 1, because it means that there has to be some kind of an edge that's going into 2, otherwise nobody would be able to reach it. So the in degree of vertex 2 in G is cannot be 0. 3 must be false. And the reason for that is that 2 is reachable in G by at least one other vertex. And that completes our questions. Hello, ladies and gentlemen. Question 8. Question 8 says, is it possible to generate a simple undirected graph with 5 vertices, each of degree 3? If yes, give an example. If no, explain why not. This is, I would personally say, a tough question, because it's not a question that has a super straightforward answer, and in a testing environment, it's hard to think outside the box like this, and this requires you to think outside the box a little bit. For some of you may find this easier than others, but we're going to go through one possible solution to this problem. I believe there's a few different ways that a few different explanations you can give for it. So let's talk to the question one part at a time. Is it possible to generate a simple undirected graph? So a simple graph, remind yourself that for a graph to be simple, it requires two things. It needs to have no self-loops, and it needs to have no parallel. I don't know how you spell parallel. Parallel? I think that's parallel. Parallel edges. Cannot have either of those things, and as long as it doesn't have either of those things, it is a simple graph. Remind yourself that a self-loop is a vertice that has an edge that goes back on itself, and a parallel edge is a vertice that has not one edge, but two edges going between a pair of vertices. I drew these with arrows, meaning this is for a directed thing, but this also goes for undirected graphs too. It just, I guess I can get rid of the arrows for simplicity's sake. Self-loop is a edge that goes back to itself, and parallel edge, two edges there. All right, so that is a simple graph, and then an undirected graph, kind of said it as we went here, but undirected graph just means that it doesn't have a starting point or an end point. You can traverse it either way. If there's an edge between U and V, then the edge can be going either direction. You can get from U to V, or you can get from V to U. So the question says, is it possible to generate a simple undirected graph with 5 vertices, each of degree 3? So let's draw out our graph. We know that we need 5 vertices in it. 1, 2, 3, 4, 5. At the beginning, when you see a question like this, I think the easiest thing to do is just to try to attempt it. We've got 5 vertices, and we're told that we want to have them each of degree 3. So let's go ahead and just try to make this graph have 5 vertices of degree 3. Let's take one and let's add 3 edges to it. Remind yourself that degree is the number of edges that are connected to a vertice. So we've got vertice 1, we throw 3 edges on it to make it so that it is of degree 3. Let's go over to 2. And let's add, it's already got 1 edge, so it just needs 2 more edges in order to get to degree 3. Let's look at vertice 3. Vertice 3, if we add 2 more edges, it allows us to get to degree 3, because now it's got 3 edges going through it. Then we've got vertice 4. Vertice 4 currently has 2 edges, so it needs 1 more. We get to 5. And now vertice 5. Vertice 5 now has 4 edges. But that's not right, because we know that each vertice needs to have degree 3. So this graph doesn't align with the requirements that we're given. So obviously there's an issue that happened here. You can keep making examples with your 5 vertices, trying to get to degree 3 over and over again. Eventually you may be able to convince yourself that, I don't know if this is actually possible. And you'd be right. This requirement, a simple undirected graph with 5 vertices each of degree 3, is not possible. But the trick to this question is trying to figure out how to explain why that is. So I'm going to minimize this, and we're going to talk about why this situation is impossible to achieve. So whenever we add an edge to a graph, when adding an edge to a graph, there is a certain number of there is a certain change that edge makes to the total number of degrees in the graph. And what I mean by that is that, let's say that you have 2 vertices in a graph, 1 and 2. If you add an edge between them, the number of degrees of 1 has gone up by 1. That's not an edge, that is, let me write it in a different color. The number of degrees of 1 has gone up by 1. So let's do plus. Plus 1. The number of degrees of 2 has gone up by 1. So if you were to add up the total number of degrees in the system, the total number of degrees in the graph has gone up by 2. Initially, it was 0 because there was no edges connected to 1 and 2, and then we added 2 more total degrees by adding that 1 edge. So in other words, make this smaller and put it underneath. When adding an edge to a graph, 2 total degrees are added. All right, so that's our first kind of part of this explanation. The second part of this explanation is looking at the requirement of what this question asks us to achieve. This question requires 5 vertices of degree 3. And so the total number of degrees that it requires, is logically 5 times 3, right? Because we've got 5 vertices and we want them all to be of degree 3. So the total number of degrees, if you were to add them up across all 5 vertices, should be 5 times 3, which is 15. So in other words, we need to achieve 15 total degrees, and we know that we get 2 total degrees when adding each edge. So in other words, if we have our empty graph at the beginning, where there are no edges yet added to the graph, every time that we add an edge, we're going to add 2 to the total number of degrees. And so we could say, we could make a little table here. We could say if there are 0 edges in the graph, we get 2 degrees. We have 2 total degrees. Say TD, total degrees, E edges. When we have 0 edges in the graph, we have 2 total degrees. When we add 1 edge to the graph, we get, when we have 0 edges in the graph, we have 0 degrees. It's an oversight on my part. When we have 1 edge in the graph, we have 2 total degrees. When we have 2 edges in the graph, we have 4 total degrees. 3 edges, blah, blah, keep going. Eventually we'll find that, I'm going to skip ahead a few numbers, that at, at 7 total degrees, we have at 7 edges, we have 14 total degrees. But at 8 edges, we have 16 total degrees. This shouldn't be a surprise. Every time that we increase our number of edges, we increase our total degrees by 2. So the total degrees is 2 times the number of edges. Because we can't have half an edge, we can never get to an odd number of total degrees. So that again for clarity. Because every time that we add an edge, we increase our total degrees by 2, we can never have an odd number of total degrees in this simple interactive graph. And so in other words, it's impossible to have a total degrees equal to 15 because 15 is odd. That's the explanation. No, it is not possible to generate a simple undirected graph with 5 vertices, each of degree 3, because the total number of degrees required is 15, and we can only have an even number of total degrees by adding edges to a graph. Hello everyone, today we're looking at question 9. Question 9 talks about union-find data structures. So before we talk about the question, let's talk a little bit about what union-find data structures are. Union-find data structures are a data structure that allows us to connect different individual objects together. So for example, let's think of the scenario in which we have 4 people. Number them 1, 2, 3, and 4. If we want to connect 1 and 2 in a group, we can do that with a union-find data structure. We can say 1 and 2 are now part of the same group. We can do that same thing with 3 and 4. and say that 3 and 4 are part of the same group. We could also say that 1 and 3 are now part of the same group. And if we do that, then the union find data structure will also know that 2 and 4 are then also part of the same group, because of the fact that 1 and 3 are together, and 1 and 2 are together, and 3 and 4 are together. So it's able to figure out that kind of transitive property of the values. So this union find data structure has two main methods that people typically use to implement it. We've got the quick union method, which is the one that this problem is going to ask us to use, but I'm going to talk about both real quick. We've also got the quick find method. The quick union method optimizes the process for union in terms of that there's two main functions that go into quick union find data structures, union and find. And so quick union will make it so that the union function is fast, and thereby being that the find function is going to be on the slower side. On the other hand, quick find is going to make it so the union function is a bit slower. But because of that, we can make the find function significantly faster. The specific way that we do this is in terms of how we link the different values in the data structure. So for example, let's take the 4 people example that we heard earlier. In a quick union approach, if we want to connect the first and the second person together, we're going to send the person 1 to and have it essentially point at person 2. We're going to have the person 2, you can think of person 2 as the leader, the source of the group. And then when we connect 3 and 4, we're going to have the same thing. 4 is going to be the leader of that group, and so we're going to have 3 be sent towards 4. Then if we were to connect 1 and 3, we would essentially have 1 be sent, we would have the source of 1 be sent to the source of 4. Sorry, to the source of 3. So we look at 1, and we look to find that the source of 1 is at 2, and then we start the arrow there, and then we look at 3, and we look at where the source of 3 is, which is 4. So we send the source of 1 to the source of 3, so we send 2 to 4, essentially. Next we have the quick find function. Think of the same 4 people. In this function, again, if we connect 1 and 2, it's just going to send 1 directly to 2. If we connect 3 and 4, it'll send 3 directly to 4, but the difference comes when we connect 1 and 3. So now in this process, when we're connecting 1 and 3, we will send 1 directly to 4, to the source of 3, which is 4, and we'll also get rid of get rid of 1's connection by doing that, and we'll send 2 also to 4. And that way now, we've done a little bit more work in the union process, but when we try to find what the source of 1, 2, or 3 is, it will be faster than the quick unions approach. Because if you were to try to find what the source of 1 was in the quick union approach, you would have to go through 2 and then go to 4. Whereas in the quick find approach, 1 is directly connected to 4 now. So each of them has different different priorities in terms of which functions we use as fastest. But in this specific question, we're asked to use the quick union approach. So we're going to be using the one on the left, right here. So the question itself says, let U be a union find data structure using the quick union approach. The union and find functions are implemented as described in the appendix section. Real quick, I want to remind you guys, if ever a question tells you that functions are described, that are implemented are described in the appendix section, use the appendix section. It will help you, I promise. It is always better to take the calls that it gives you and manually input it into the algorithm that it gives you, because oftentimes algorithms can be implemented in different ways based on how the developer chooses to do it. And so it's really helpful to be able to manually put through your information to make sure you're checking your work. Even if you are 100% positive you know how the data structure works, it's never a bad idea to check your work if you've got the time for it. Question goes on to say, U has 10 items numbered 0 through 9. Show the initial state of U and its respective state after the following calls, and then it gives several union calls. So, the underlying data structure that goes with these union find data structures is an array. This array, in this case, it goes from 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so it's an array with each of these indexes and then a value at each index. And the starting values for each of these indexes is the index itself. So at index 0, you're going to have value 0. At index 1, you're going to have value 1. Index 2, you're going to have value 2, sorry. So we continue on, and we look at the first call that was made, union 5, 2. Now, if you were doing the exam yourself, you would be able to look back on what the function union is in the book, at the back of the book. I'm going to write it down here so that we can keep track of it ourselves. Function union of PQ is IDP equals find P IDQ equals find Q ID of IDP equals IDQ, and then we've got a count equals count to minus 1. Count is just the number of groups in the union structure, in the union find structure. It's not relevant to this problem, what our count is, so we'll ignore that when we're running this algorithm. So this algorithm, you might notice, also asks us to call find. So I'm also going to write out find real quick. Function find of P is while P does not equal ID of P, P equals ID of P, and then return P. So let's go ahead and make our first call, and we'll go through this function as we go. So union of 5, 2. This sets the P for union to be 5 and the 2 for union to be Q. And so the first line we're going to do is IDP equals find P. So IDP equals find 5. So we go ahead and go to the find function, find 5. It says while 5 does not equal ID of 5, then we set P equal to ID of 5. So essentially, what this whole find function is doing, you really don't need to run through this find function manually because it's fairly simple when you get the hang of it, in that the find function goes through each index in the array, and it checks, is the index equal to the value of that index, at that index? If it's not, let's take that value and let's use it as our new index, and go to check the value at that index. And we keep going until we find an index that has its value set as itself. So here, we're doing find of 5. We want to check, is 5, ooh, what is that? This is computer science, we don't need a ruler. Okay, there we go. We want to look at the array at index 5. We want to see, is the value at 5 equal to the index? Yes, 5 is equal to 5. So we go ahead and we go back and we set IDP equal to 5. We now do the same thing for IDQ. IDQ equals find of Q, so find of 2. And we go to the array at index 2 and we see, is the index at 2 equal to 2, equal to its value? Yes. So we go ahead and set IDQ equal to 2. And then we go here and we say, is ID of IDP, or sorry, not is, ID of IDP, go ahead and set it to IDQ. So ID of 5, set it to 2. So we go into the array which is called ID, and we erase the 5 and we set it to 2. Beautiful. We're now going to go on to our next call given, which is union 7, 9. Union 7, 9, we do the same thing. Our 7 is our P, our 9 is our Q. IDP equals find 7. So we go to index array 7, array index 7, and we check if it's equal to its own value. So 7 is equal to 7, so we go ahead and return the 7. Next we do the same thing with Q. So 9, IDQ equals find of 9. So we go to the index 9, we check if it's equal to its value. They are. So we go ahead and set that equal to 9. So now we have ID of 7 equals 9. ID of P equals IDQ. So ID at 7 equals 9. Good stuff. Let's keep going. Should mark these off as we get to them. We did that. Next we have union of 0, 1. So 0 is our P, 1 is our Q. IDP equals find of 0. So we look at array index 0. We see, is it equal to 0? Yes, it is. Is the value equal to 0? It is. So we set IDP to 0. Then we go to IDQ equals find Q. So IDQ equals find 1. We check, is the value at the array index 1 equal to 1? Yes, it is. So 1 equals IDQ. ID of IDP equals IDQ. So ID of 0 equals 1. You'll notice for all these I've been skipping the count line because, as I said, it's important if you want to know how many groups you have in your array, but we don't really care about that, so we're not going to even mess with keeping track of it. Next we have union of 4, 5. So we have P is equal to 4, 5 is equal to Q. IDP equals find of 4. So we go ahead and check the index array index 4. We see, is the value at array index 4 equal to 4? Yes, they are. So we go ahead and set 4 equal to the IDP. Now, this IDQ line is the first non-trivial find function we're going to have so far. In that, so far, every time that we call find of P, it's just returning as P. But this time we're going to get something different. So our Q is 0. Sorry, our Q is 5. So we're going to do find of 5, find of Q, find of 5 is equal to IDQ. When we do find of 5, it says while 5 is not equal to the ID at 5. So let's check. The array index 5, its value is 2. 2 is not equal to 5. The index and its value are not equal. So we take the value and we go to the index with that value. We go to 2. We look at 5, we see that it's not equal to its value, so we take that value and we use it as our new index. Then we go to 2, we check, is 2 equal to its value? Yes, it is. 2 and 2 are equal, so we return the 2. So now, ID of IDP, so ID of 4 equals 2. So we're going to replace the 4 with 2. Next we have union of 8, 1. So IDP equals find of 8. So we're going to go to index 8, see is it equal to its value? It is. So we set IDP to be 8. Then we do IDQ equals find of 1. We go to 1, we see is it equal to its value? Yes, it's equal to its value of 1, so we go ahead and return 1. ID of IDP, ID of 8 equals IDQ. So ID of 8 equals 1. that line up? All right. And then we have our one last call, union of 3, 0. So our P is 3, and our Q is 0, so ID P equals find of 3. 3 is the, we look at 3 index and we check if it's equal to its value. It is. So we go ahead and set IDP to 3. Next we have 0. We check, we do find of 0, so we're going to check the index 0. We're going to see, is it equal to its value? No. Find of 0 finds that the 0 index is not equal to its value of 1. So we go to the index with that value of 1, and we check again. Is 1 equal to its value 1? Yes, it is. So we go ahead and return value 1. ID of IDP equals IDQ, so ID of 3 equals 1. So we go ahead and replace 3 with 1. And that is our last call in the union set, and so this is our final array that we get. Keep in mind that when you are doing this problem for yourself on the exam, it states in the problem that it wants you to show the initial state of U and its respective state after each call. So not only should you have this final array, but you should also have all of the arrays for the in-between steps at the beginning.